Experts, Ryan Olson. Ryan, why don't we start a little bit? So, I know a lot of times at trade shows people are running just sort of video clips as demos, but we're actually running live here. So maybe start with the Volta V100.
Sure, absolutely.
Talk a little bit about that and the DGX station.
Sure, absolutely. So on display here is our new DGX station. So it's got 4 of our latest V100 GPUs in it. And what's really cool about this demo is we're running live on Volta. So this thing exists, it works, and it's really fast. What we're comparing here in this demo is inference. So this is time's the solution for inference. So this is, once you've built a model and you're ready to create an application, we have a product called TensorRT that optimizes that for real-time inference. So that TensorRT in real time. On display here, we got model for TensorFlow running live on Google Cloud, performing inference on CPU using TensorFlow. We take that exact same model, we run it through the TensorRT compiler, optimize it for V100, and that's what we're running here live on.
So just to be clear, when we're running on the Google Cloud, obviously we're running on Xeon type CPU, like a normal compute cloud instance. We're not running on this laptop, for example.
No, exactly. We're running on Intel's latest Skylake CPU on Google Cloud.
Okay, Skylake. Okay.
Skylake.
Right. So, what types of real-world applications would this be, and what type of speed-ups are we getting with the DGX station?
Okay, so TensorRT, the new version of TensorRT does 3 things that's really important. One is it optimizes for inference. So inference, once we compile this down, it's really valuable for things like automotive, because the time to solution, or that latency window, is basically your reaction time on decision making in a car. So you want to be as fast as possible, but you also want to run as big of a network as possible to be more accurate. So TensorRT does both of those things. It optimizes performance and gets you this kind of throughput result.
So let's look at this Google Cloud, right? So Google Cloud, and this is in the demo, it looks like we're recognizing pictures of flowers. So let's say you had a website and you had, people were uploading pictures of flowers to it. If you're running on Google Cloud, you could recognize.
So this refresh we're seeing here, that's actually from the processing. Yeah. It's not some artifact in the display.
Exactly.
Okay. So that gives us a good idea of the speed ups.
Google Cloud, it's running 4 images per second.
Yeah, about 4 or 5.
And this one seems to be doing maybe a row or something.
Down at the bottom, 512 per second.
Images, so that's maybe the whole screen.
Yeah, that's
half the screen.
That's about 120 times faster than Google Cloud.
And that's just the single DGX station.
That's a single GPU inside it. So if we're using all 4 GPUs in parallel, we could be doing 2,000.
So is there any?
In fact, we could do even better. We're only using about 1/3 of one of
Is that because of the demo purposes you're using your one card?
Yeah, exactly.
Okay.
Yeah, we just wanted to highlight what V100 was capable of.
Okay, that's quite interesting, because you're selling that thing as a complete box, so the people are going to use all 4.
Well, from a visual perspective, we couldn't even display it. It would be going so fast.
Okay. That's sensible. Yeah. Sensible PR stuff for the interview.
In fact, we had to take one of the largest networks that we could find to slow this down to a human comprehensible time frame.
Sure.
Like if there was a pre-trained ResNet 1000, I would have used it.
Yeah.
So.
No, mate, yeah, sure, that makes sense. Okay, so this is the inference demo, and we're doing maybe the 512 versus, how many is that one on there? Because we can't really see that one. What's the count on that one?
4.8.
Okay. So Volta works.
Volta works.
Great.
So
let's move on.
The 2 other things I want to point out about this, one is we can now take TensorFlow models and convert them using TensorRT. Before it was just Caffe models and our C++ API. Now TensorFlow is super popular, so we added support for TensorFlow, and we're adding support for other frameworks as we move forward. The other thing that we added with TensorRT 3 is Python bindings. So Python bindings allow us to build these kind of applications really quickly. So this is the gRPC backend, so it's written in Python. Using that, we could just very quickly, within a few hundred lines of code, develop a client-server model. And so that's just like the expressive power of Python. And plus, this kind of community really likes to use Python. So
yeah, sure. That's a sensible way to go with the Python. Okay, so what else? What other toys we have here?
So this is one of the demos we ran at SIGGRAPH last week, and these are always really popular with the audience. So this is a great example of deep learning being used for graphics. And what this is doing is using a deep neural network to do style transfer. So we're taking a real-time video here, stream, that you're taking a picture of, and then we're feeding that into a deep neural network and comparing it to another pre-painted image. So there's sort of the abstract impressionist picture.
So you're taking, you're taking a pre-prepared material, applying that style to a live transform.
Right. So Ryan,
okay, because when I first walked past, I thought you were just applying the stylized effect using
in fact,
physics.
Change the style, and there we go. That's more of a.
Okay, so you're changing the artist, and the GPU is basically tracing the art onto the live feed.
Yeah, so the GPU is learning the features of the artwork and then trying to apply those, transfer those to the image that it sees from the camera.
So let's say we put a photo in there. How would the results come up? It wouldn't be that clear, would it?
It would just be a still image of as an input photo.
Yeah.
So it would just be a snapshot, like one frame of this 30 frame per second 4K video feed that we have.
Yeah, I'm sorry. I mean, so instead we put art in. We put a photo in, a still photo.
It still kind of works.
Yeah, but I'm saying with the effect, would it be more like, it would be as appealing as that? Because art is brush strokes and sharpness. It would be,
exactly.
It would just be a blur of color, would it?
Exactly.
Okay.
We did a style transfer demo at GTC that does kind of lifelike ones, and so that uses some work from Cornell and Adobe.
Okay.
Adobe, that really kind of showed off what you could do with realistic photo transfer.
Okay, Ryan. So this is not really running that fast. All right, that's reasonable. I mean, we're doing 4K. What do we need? What would we need to speed it up? Obviously, other than Volta. I mean, that's the obvious answer. What is it? Because the algorithm is intensive, or you're running it on one card? What's the bottleneck here?
It's pretty damn fast for a 4K.
Yeah, it's actually really fast for a 4K.
This is really fast.
Actually, we're somewhat limited only because the transfer card isn't as good. Like, we've got it down to lower latency, but that's only because we're not feeding the GPUs fast enough.
So optimization, basically.
Yeah.
Okay.
And we actually, if we ran this through TensorRT and actually use this as a TensorRT model, we could make it even better. We could probably get away with using less hardware to do the same kind of effect.
So AI imitating art. So what type of other demos can we do with this sort of algorithm, this sort of system?
This is just kind of a fun one that highlights what we can do. In the talk, we have some generative models.
So over here we have a demo of our software stack and set of APIs called Metropolis. Metropolis is really all about building smarter cities with AI. And again, here what you're seeing is 30 HD channels being decoded, real-time data analytics being pulled off it, and then extracting metadata off it. Now what's really amazing is that this is again all inference, and this isn't being done on a large 300-watt GPU. These 30 frames are done on this very small 50-watt P4 card. So the P4 is designed to fit in virtually any server.
So to our audience, just you're doing this for compute. This is not using the NVIDIA engine to decode video.
No, it is. So that's one of the benefits. Again, and all of our GPUs have both the CUDA cores that are used for deep learning and inference, and then it also has a built-in video encoder and decoder. So that's why we're able to do 30 HD channels in decode. If you were on a typical CPU-only server, you can typically only decode a couple of streams at a time.
And so we're doing 30 streams here, so that would be the limit for the smaller card. And we have to scale up, obviously, if we want more streams.
This particular demo with what we're doing here, this is running at 30.
Okay.
The limit.
So what would we be using this for? This would be, for example, I don't know, some standalone analysis.
Well, Today, there's about 500 million video cameras in the world used for
I was close.
right? As I was walking across the street here to the convention center, I saw there was a sign saying this is under video surveillance, right? And it probably went back to a police station where, if you're lucky, there was a policeman that was awake looking at.
We've toured the center. There's only like 5 screens there.
And the problem is,
it's nothing like this.
If you're looking at these 30 screens and you're trying to answer the question, when does the white Toyota Camry with a license plate that starts with XYZ come across the screen, you'd be pretty lucky to find it.
So as we've seen in previous NVIDIA keynotes, with this demo, with these streams, you are taking the video, you're doing number plate matching, you're extracting the number all in the compute of the card.
Exactly. In the inference calculation, we're not only classifying what the objects are, car, truck, license plate, but then we're also able to extract information like the license plate number.
So in this demo, so it's highlighting different, it's only doing the cars in this demo. So which cars, which is it?
Every red box is identifying a different object. In this case, it's a car.
Okay, and how far does it go? Did you just say, for example, there's a RAM, that one, and that's a camera? In this demo, what's the context? Just that much detail, or does it go further?
It can be as much detail as you want to program.
It depends on how much power you have, but I'm saying for this demo though.
And how you've trained your network. So on the other side, we have a little bit more details of this one.
I'm just very impressed. I'm very impressed you're able to do it on the smaller wattage core.
Oh, we can go even smaller on the other side.
Even smaller. Let's go take a look.
So you're just doing and then you're also grabbing license plate or not license plate.
So this demo is running on our embedded platform, our Jetson platform. Here what you see is our TX2 development kit. We're actually selling these at the show for $599 Australian, if anyone wants to buy one while they're at the show.
I think my audience want to buy a Volta.
This is a fully integrated system for development for embedded applications. So if you wanted to build a smart drone or a camera controller or other object, you'd use this as your development kit. And then this is actually the brains behind it. This is the TX2 module. So as you go to volume production, you'd buy this small credit card size module, and then you'd work with your own electronics provider to make a custom board that had only the features you need for.
Does this form factor have a specific name? Like for example, you have the SMX2 in does that one have a name or?
TX2.
This TX2 module. Now, to see what actually we're able to extract using this part, which is about 10 watts, Ryan, you want to walk through it?
Yeah, so like you saw over there, you were highlighting, you kind of asked what other things were you extracting, and this kind of shows a very similar design or a similar network between them. So here you can see we're also finding cars.
We had more boxes, I think, in the other one. This is a bit more specific.
This is a bit more specific.
Okay, that makes more sense.
A bit of a smaller one, but you can see here we're figuring out the color and type of car that's being run, and we're also detecting license plate or not a license plate.
So these samples on the right, they're the frame grabs, or that's from your network?
Yep, those are kind of frame grabs as it's going across. It detects a new one, and so grabs
and the samples in the network are something different. It just matches them.
Yes.
Okay.
Exactly. And so over here is also for faces. You can see as people walk into the field of view of the camera, we're looking for faces of a particular size. So once it reaches a particular size, we grab it. You'll see it when it's grabbed with the bounding box. And those images are put through a different network, and some features are extracted. So the features of interest here are gender, eyeglasses or not, eyes open or closed, beard. And so you can imagine that if you wanted to do object tracking through multiple cameras, you would generate a feature vector of me. And my feature vector would be consistent as long as the same network is running in these different cameras. And so you could say, like, I want to follow that feature vector as it moves through a scene. And that's one way that this could be used.
And there are actual systems out there deployed using this technology and this software and these algorithms. To the best of what you can say, I'm saying these type of systems are out there.
And we have a number of different partners around the world that go through and integrate these. One of them, Heike Vision out of China, is one of our big intelligent video analytics partners, and a number of others as well.
Yep. So again, this software and algorithm is basically optimization of bottleneck and compute bottleneck. So if you want to run it on 10-watt part, you only have to do certain matching. If you want to run it on, say, 4 voltas, you can do so much, is it?
Yep, exactly. Okay. So you kind of tune your network and you tune what you want to get. And
you make a good point, because usually when someone thinks about compute, they think about running the same software on one-to-many cores. We don't usually think about scaling, turning the knob to scale it up and down.
Sure, absolutely.
DGX Station it was not a commercial product before, so it was announced as a Volta product.
Yeah.
2 things to remember about DGX Station. One is, of course, from the hardware level, right? It has 4 Tesla V100s packed into it, liquid cooled, so it's whisper quiet, right? This is actually running the demo we saw earlier, and virtually no noise coming out of it. Secondly, it's one of the only workstation packages where you actually get the V100 and you get NVLink. So all of these 4 GPUs are connected with NVLink. So
and this is the 2nd generation NVLink.
Absolutely. So NVLink with Volta is NVLink 2.
So obviously this is supposed to sit on the desk, but now you've updated the DGX1 as well, Volta. So how do these compare? So somebody would use this from this desk for like prototyping, experimentation, versus they would put the DGX1 in their rack, or?
Absolutely. So DGX1 is a server, it needs to go into a data center.
So DGX1 has 4 GPUs, and your competitor just now has announced a full rack of them with 1 petaflop. So a bit of filling a rack with DGX1 is a bit of a strange proposition, considering you've made them to put in small quantities.
Well, no, we have a number of customers that have deployed DGX1 in large quantities. So NVIDIA itself,
because usually we see the Dells and the custom with the P100s and that sort of thing in terms of a compute farm versus the DGX1, where you made it for us sort of semi-custom.
Well, so of course NVIDIA itself has a large compute farm of DGX1 servers.
Sure.
That's a system we call Saturn V, which is 124 DGXs, and that's what we use internally for development. Now, actually at GTC, Facebook AI Research, or FAIR, also did a presentation, and they talked about their cluster that they're running 128 DGX1. So again, a number of customers out there running multiple systems. So what you have to remember about DGX is 2 things about it. Besides great hardware, is also the software. What comes with it is NVIDIA optimized versions of all the common frameworks. TensorFlow, MXNet, Microsoft's Cognitive Toolkit, and they're optimized and installed by NVIDIA using a Docker container technology.
Yeah.
And so our customers have access to a private repository where they can go in and get the latest optimized versions.
As I think some people will be aware, it's a Linux workstation fully supported and optimized of NVIDIA.
Exactly.
What about the Windows support? So would those want to run the Windows server, or those doing the experimentation on the Windows?
Well, if you want to run Windows, you can certainly run in Azure Cloud, and all of our OEMs would be more than happy to ship you a Windows-based server. So again, we've focused on Ubuntu with this particular platform, but again, because the software is delivered is in a container, it could very easily run on
just to switch back to hardware, so this is the first Tesla with display outputs.
Well, because in a workstation, you typically want to see the display outputs, right? So again,
But usually Tesla people don't want to see the output anyway. They're running the compute, so...
Right. Well, again, in a workstation environment, right, it's logical that you want to be able to go through and see it. There's a lot of applications where you want to visualize the outputs. And
is that because the compute loads are becoming so complex that the visuals... Say you're doing a fluid, particles or fluid or something, and you have such a rich visualization, it's become time that, say you have a small display cut, it's not really going to cut it, is it?
Increasingly, people want to do what's called in situ visualization, right? The data sets are so big that you don't want to move them to visualize them.
Don't you think there's going to be some crossover with Quadro then, especially with the bigger Quadros?
Well, we already have our grid software, and our grid software runs on top of Tesla GPUs. So that lets you run, in a Tesla-based GPU, and then add remote visualization to that.
So, I'm happy to see that this one here that it works. It's not just the show thing. It looks pretty complete to me. So let's round this talk off with just a description of the Volta architecture as is. We're not talking about anything in the future. We're doing AI to graphics. We've had one demo already of the ray tracing denoising. Is that going to be the future? I mean, do you think from a research point of view there's going to be a lot of things from AI that is going to power graphics, especially with new GPUs like this?
Absolutely.
I think that answer pretty much, I think that rounds it off. I think people can make what they want from that. So in terms of my audience, who more the GeForce, I think we're going to be pretty impressed. Yeah.
Great.
We're going to be pretty impressed with what comes in when we bring this down to market, is it?
Yeah.
Okay, Mark. I'll take that under advisement.
Well, you can place your order now, so any of our customers.
So that's interesting. So this is on sale now.
It's on sale, right?
In all region, or
yes.
Okay.
DGX1.
And that's from NVIDIA directly.
It's
or from the high performance partner.
DGX1 is always sold through our NVIDIA partner network.
Yeah, and this one?
And as is DGX Station.
Okay. Thank you, Mark.